There's a few.
All right, let's take it easy today. Not do too much work.
Hold it.
Okay, so an action is the group in action. It means the group is actually doing. Look at that. Could put the camera there. There are two more screens that you can watch at the back.
The distance might cause problems, though. If you can move that to there.
Distance.
Yeah.
Why?
It just says that we can look up there if we want to.
Oh, right. But behind us.
Yeah,
Oh,
maybe
right,
we should all sit in the back there.
It's off to the back.
Oh no, but I couldn't because that thing is not there.
Yeah.
So that's the problem. Yeah, so think of the group doing something to a set. Like, the good examples are not the ones that the book writes. Okay. So for instance, you can say that if you take the general linear group, which is matrices, okay, it's matrices, but every matrix in linear algebra is really a transformation, a linear mapping on some vector space. Okay, this is what matrices are good for. So they act like this. So you take a finite coordinates x and y, and you just multiply it with the matrix, and you get the finite. In this particular example, these coordinates. So this is how you should see the group. But yeah, so this is what one matrix does, but the idea of the action is that they compose. These actions compose in the same way as the group elements multiply. Okay, so every element of the group, okay, so the way this is written, the definition is that you have a mapping that takes an element of the group and an element of the set X. And that gives you something in the set X. Okay. Well, another way you can look at it is you fix G, one element of the group, and that does something to X's, so it moves X's around. That's another way. You need both ways, so it's kind of a different point of view. And then how these things compose, for every fixed G, you get a mapping, and these mappings compose, and they compose in exactly the same way as the elements of the group. So that's the idea of a group action. And then we said that somewhere I said that what this G does, there was this note that I forgot. Okay, so when you fix G, you look at this mapping, which takes X and moves it to what the G does to it. It's a permutation of the set X. Okay, because otherwise it couldn't work. I mean, you need inverses to act inversely to what this does. You need the inverse mapping to this. And if you want the inverse mapping, necessarily you need permutation or bijection. So, otherwise, you couldn't have an inverse. And then we said that there are some examples that will be useful later. And those are these two. Nap by multiplication. So this is in a case where the group acts on itself. Okay. So the set X is the same set as the group. It's somewhat confusing perhaps, but this is what it is. And you can check, and I told you, I think, you check that all these axioms, well, two conditions from the definition are satisfied really with these actions. And trivial to check. And then another one is where you take a subgroup of the group and that acts on the whole group by conjugation. So they said X is the whole group, you pick a subgroup. And every element of the subgroup acts on G, like this. And Now this is the product in the group action. Written down. Okay, then we said that if there is something that moves x and y, we say that x and y are G equivalent. You know, we should really not be saying just G equivalent, but G and that action equivalent. But this is what is used. And we said that calling it equivalent is justified because it really is an equivalence relation. And then we said that these the equivalence classes are called orbits. Okay? So the whole set X is partitioned into what's called orbits. And Jordan said that he had the feeling that these orbits should all be the same size, not the same size. But they're not, and that's where we ended. Okay. And the reason that they don't have to be the same size is you look at any element. Okay. So what? So there is at least one element of the group which maps it to itself, which sends it to itself, and that's the identity, because the identity sends everything to itself. Okay? The identity just sends everything to itself. And then you might think that everything else sends it somewhere else, and that creates the orbit. Okay, so you look at one element of the group, it sends it there, another element sends it there, another element sends it there. But it could happen that there is not just the identity that leaves it in place. There could be many more elements that leave it and don't move it. And in a different orbit, there could be a different set of elements that leave the elements untouched. Okay, so we're going on to prove something, I think. So this was the definition of the drift. And there's an important bit hidden there. The book calls an orbit O, big O sub. The index is the element whose orbit it is. Okay. So of course OX is, well, not always, but in many cases it's OX is OY is OZ is O something else, because X is not alone in the orbit. So you'll have different notations for the same. It's also good. That was just revising because I'm too lazy to do much today. Okay. Then if you look in the book, it's there's an example for 14.7. Okay, so we'll do it for 14.7. It's a slow example. Here's where you have, well, a permutation group which has 1, 2, 3, 1, 3, 2, and 4, 5, and 1, 2, 3, 4, 5, and 1, 3, 2, 4, 5. These are all the elements of the group. Okay, you could say it's generated by 1, 2, 3, and 4, 5. Generated by these two elements. And there's a subgroup of 5. Symmetric group. But permutations of 5 elements, the natural thing that it should act on is a set of 5 elements, right? So acting on 1, 2, 3, 4, 5. So every element of G is a permutation, and that is exactly the permutation that is the permutation in that action. So in this case, and so what is the orbit of 1? where can one get sent by these permutations when you only look at these permutations? So how many elements in the orbit?
Including one, right?
Yeah. Exactly. So you need to include one. Everything okay? There in the middle? No?
Don't get it yet, but I might do anyway.
Okay. So I'm looking at, so I have this group, okay? I'm looking at where it's sending one. So this permutation sends 1 to 1. This permutation sends it to 2. This permutation sends it to 3. This permutation sends it to 1. This permutation sends it to 2. And this permutation sends it to 3. So the elements where I can map, where I can send 1 using this group are 1, 2, and 3. Okay, so this is the idea of orbits. What is the orbit of 2? Well, obviously, because so now actually, when you've got an orbit, yeah, because we said that it was an equivalence relation, G equivalent and equivalent relation. When you've got an orbit, it's the orbit of all its elements. It must be the same, because an orbit is an equivalence class, so you can't get overlapping orbits that wouldn't be the same. Okay, so the orbit of 2 and the orbit of 3 are the same. And then what is the orbit of 4? Oh, so give me a permutation on this list that sends 4 to 1.
If you were to kick 4, 5 with 4, 5, that would be an inverse, and that would give you the identity, wouldn't it?
Oh,
yeah,
it's very similar.
Never mind.
Okay, problem solved.
Yeah.
Good. So it's 4 and 5. Which of course must be the orbit of 5 as well. Okay?
Yeah.
This is the idea. Good. You get it. I'm making an example extra. Not in the book. Oh, maybe it's one of the exercises. Maybe it's one of the submission exercises. So let's do it.
Maybe it's not. That's right.
So what I want? I want G to be the group of all rotations of the plane. Rotations of the plane about the origin. Okay. So somehow this is isomorphic to the additive group of the real numbers modulo 2 pi. Yeah, or modulo 360 degrees if you prefer that. But normally you'd say 2 pi. Not going to think about that. Okay. So what does it do? So this is the theorem, and you look at the point in the plane, and in the rotation, you just look at a circle. You just send it along the circle by some angle theta. Okay, so this is what it does to points. And depending on what angle you take, that for any angle between 0 and up to 3, and not including 360 degrees, any real gives you a rotation or not. Yeah, sounds reasonably easy. So, so this is acting on R squared. Well, it could be acting on many other things as well, but I'm looking at the action this does on R squared, which is rotating things. And what are the orbits? So, for example, what is the orbit of the origin? So, by rotating about the origin, where can I map the origin? The origin over here. Okay, so this is an orbit which only has one element. And then, so what happens with this point? I'll call it X. Where can it get mapped?
Circle points around the origin.
Yeah, so that's the circle that around the origin, that centered in the origin, where X is on. This is exactly. So if you want to write it, you can say that this is all the points in the plane whose distance from the origin is the same as X's distance from the origin. Okay. So these are the orbits. There's a slightly different example to that one, because here we have infinitely many orbits, and almost all of them are infinitely long. So that's my example. Do you like it? In fact, it's a subgroup of the general linear. Because each of these rotations you can express as a matrix. Actually, matrix is determined at once, so it can be a subgroup of the special linear. Where is my pile of spare things? Is it there? Okay, I'll take the handouts. Okay, any questions so far? Just as a test question, what are the orbits when you take the general linear group? Yes. Example extra plus. The general linear group acting on the plane. So these are not just rotations now, but they're all linear mapping. So what are the orbits here? I don't think so. But it's very close to it. Okay,
Oh,
so
I mean, so yeah, you'd still have the origin one that can't be moved by him.
everything else is. What do you say? So the origin you can't move. Okay, so the orbit of the origin is, well, contains the origin. Is there anything else there? Or can you push something else to the origin? No.
Make every point on it.
Can you move a point to the origin? That is not the origin. So. No, why
Oh
not?
no, because the matrix will do it, but it isn't determined. It does really linear.
That doesn't have to have determinant one.
Spatial linear
Oh.
has our determinant one as
Well, it has to have non-zero determinant.
Yeah.
So you can't put. So you can't do much. So when you so there are several ways to prove that there is nothing else, and then there's another orbit which is the rest. So x is everything else than the origin for. Because you can always map any point that is non-zero to any other point that is non-zero using linear transformation, but you can't put anything to zero. Well, one thing is that we said that each of the little actions by every element is a permutation bijection. So 0 is mapped to 0. There can't be anything else that's mapped to 0 because it's injective. Okay, but that's assuming that it's an action, which we didn't really prove, but it is. And well, if you wanted to get it directly from the matrices, and you say, okay, it's x, y, I get something. What do I get? Ax plus by. Cx plus dy. Okay, you want this to be 0. Well, if you're solving the system of equations, then and if you want this, so one solution is x, y, and from linear algebra, you kind of know that the determinant is non-zero, then you get exactly one solution. Hopefully. So maybe you do these. Did you do the? I think it's grammar school or something like that, where you can get the solutions for a system of equations when you do the determinant. So you take the determinant of this, and that's the denominator, and then you replace one with the right-hand side, and leave the other one there. You get one solution, and then you replace the other one with the right-hand side, and you get the other one. In any case, if the determinant of these coefficients in the system, the determinant is non-zero, we get exactly one solution.
After the exam,
I think I've done that. I'm gonna skip.
Well, linear algebra, every group is a group of matrices. That's got groups, but we won't get there, unfortunately. Okay, so that's another example. That was quite fun. But we should move on, perhaps. Successfully procrastinating. Definitions. All these definitions always start like G act on X. Okay, the book says X is a G set or a G is an X set or something like that. No, X is a G set, but that's a strange terminology. But this is so I always say G acts on X. And then if I take any element of the group, and I look at all the X's which stay put, And I call this the fixed point set of that element. Okay, and second definition is confusingly similar. G sub little x is all the elements of G this is called the stabilizer. Thanks. Okay. Sometimes to pass it. There are two things that look quite similar, but they're very different. One of them is when I look at an element of G, so one permutation of X really is what I'm looking, and I look at all the fixed points of that permutation. So I'm looking at all the points that don't move under this permutation. Okay, and that's the fixed point set of that particular G seen as a permutation of X. And the other one is I look at one point of set X that is being active, and then I look at all the group elements that leave it. And that's the G sub X is a subset of G, and X sub G is a subset of X. Okay. Then I have in my notes example 14.9. Read it, but it doesn't shed much light. I can't remember what. So yeah, so I think we get. I think that's. Okay, but if we look at some of the examples we had, so here we have. I'm trying to keep everything. I'm not really successful in this. Okay, look at this. So if you look at what's the stabilizer of 1, for example, that means find all the permutations in G that where 1 stays put. You get 1, that doesn't move 1, that's the identity. 4, 5, and that's it. That's the same for 2 and 3. And then for 4 and 5, you get that 1, 1, 2, 3, and 1, 3, 2. Those are the permutations. This would be the stabilizer. You notice anything interesting? Okay. Now here, what's the stabilizer of 0? The origin? Everything. The whole group G is the stabilizer because nothing in the group moves the origin anywhere. What's the stabilizer of any other point than the origin? Triple. And finally, yeah. What's the stabilizer? Well, similar, right? So 0 is stabilized by everything. And it moves. And for the other ones. So take it as me. But there will often be more. But I don't know. I don't know the answer. It's a bit embarrassing. I'm talking through. Okay, so there will be more. So, for example, if you take a point, so there are these things that just expand like this. No. Anyway, I think there will be more. I think you can have linear transformation, but keep taking. Maybe. Yeah. So, for example,
Yeah, if you're at any point on just one, if you're on an axis line, your point's already on an axis line, and you have transformation. No.
yeah. So, for example, if you take 2, 1, like this. So what it does is it doubles the x. Right? So when you act on a point with coordinates x, y, you get 2x, y. So if x is 0, it stays put, no matter what y is. So there is more to it. Well, I don't know. No, so let's move on and leave it open. So that's,
Those fixed point and stabilizers are just
right, so it's
lots of fixed points.
oh, the fixed point set. Okay, that's right. So that's a different thing, and it's not as important for what is coming now. So what it is you look at all the elements of the group. So think of all the permutations that all the little transformations of x, and you look at all of them that don't move x. No, that's sorry. No, you look at one. I'm back to where I apologize. Forget the past 20 seconds. Now, yeah. So you pick one particular transformation, and you look at all the points that it doesn't move anywhere. Okay. So if you look at one particular transformation, given by this matrix, points that don't move anywhere are the points exactly the points where x is 0 and y can be anything. So in this case, it's so in this case the fixed point set. What this is no point like that. So all the things where x is 0 and y is. Done. So maybe I'm going slower than actually is necessary. Okay. That's but this one is easy. So it's a proposition. Did you notice anything interesting about the things, the stabilizers that we were looking at? So the proposition says that when I pick a point in x and I look at its stabilizer, is always a subgroup of the group G. Yeah. So in all those cases, we looked at, we had a subgroup. That, which you can go back, you can check. And the proof of this is, okay, so how do you prove that something is a subgroup? The repeating topic. Against the identity, okay, so what is EX? So E stabilizes X. So E is in stabilizer. What else? Okay. Closure under what? the two closures. And under the multiplication and then undertaking inverses. So two different closures. Okay, so if G1 and G2 are in the stabilizer, that means that so now I want G1, G2. So what is G1, G2 on X? Well, by one of the, you don't really have to be writing it so, because one of the conditions was this kind of, not really associativity, but kind of associativity, because the G1, G2 dot here is not the same as the G2X. That's G2 acting on the set X, whereas this is the group multiplication. So strictly speaking, different operations. But G2 stabilizes X, so this is the same as G1X, and G1 stabilizes X, which is yeah. So this, and so G1, G2, the product is also in the stabilizer. Okay, and then the inverse. So if G is in the stabilizer, okay, there was a note which said that we should prove this as an exercise. So this means that Gx is X. Okay, how do you prove that G? So what is G inverse?
It's stating there that GX is not equal to X.
Oh, that's
Right, sorry.
that's an error. Okay, I should put that. No, I'm sorry.
You just put in for the G inverse X and substitute in Gx, then you have G inverse Gx.
Yeah.
So,
Which I can do because X is the same as Gx. So X can be replaced with Gx. Exactly. So that's that. Now, we're coming to the kind of thing. Well, I don't think I have enough time for the proof. So apparently there was a meeting of the dean of the faculty, who's now called the provost chancellor, with student reps, and one of the first year student reps complained that Killian's lectures are proof upon proof.
In first year, second year, yeah.
I got it first year. I think I was finished with first year.
But then, like,
But why is that a bad
yeah,
thing?
there's nothing wrong with it whatsoever. If anything, I actually appreciate them more now than I did then.
Okay, so let G be a finite group. I don't think you actually need these things. Acting on a finite set X. And we pick one element of this. And then what I'm claiming is that the orbit of X, the size of this orbit, is equal to the index of the stabilizer in G. Okay, so what's that mean?
Size of
So this is x. Okay, here somewhere we have x, and these are all the other points that x can be moved to by the elements of the group. Obviously, x can also be moved to itself by the element. Now, I'm coming back again to what I said to Jordan. It was a brilliant comment because it's a brilliant comment. He said that the orbits should all be the same, but they're not because they're slightly dependent on stabilizer. Okay? And I'm coming back again to it. So if the stabilizer is trivial, stabilizer only contains the identity, then every other element of G moves x somewhere else, and then you get the orbit will be the same size as the group. Because every element of the group moves x somewhere else. Okay? And that's only if the stabilizer is all we want to. Just a trivial. Now, if the stabilizer, say, has two elements, what happens is you have two elements moving x there, and then necessarily, because it's a group, you have two elements moving to this point, and you have two elements of the group moving to this point, and you have two elements moving to this point. Because if you have one element moving there, and you multiply that element with the other thing in the stabilizer, you still move it back. Okay, so this is just a side of mine, really. But if you have G in the stabilizer of x, and then you have some G dashed, which, well, G dash takes x to some other element. Then what does G, when you multiply G dashed by G, well, this has to move it to G dash Gx, but then Gx is still x. So this moves it to the same element. Okay? Okay, let's say I have something in the stabilizer. And let's say it's something else in the identity. But what it means for the stabilizer, for G to be the stabilizer, it means that Gx, so the actual G on x, gives you x. Doesn't move x away. Now if you have some other element that moves x over here, you take that element that moves x over here and multiply it by something on the stabilizer, and this new element of the group also moves it back. Yeah? So for example, if you have two elements in the stabilizer, and there are two elements of the group that move x here, and there are another two elements that move x here, and there are another two elements that move x here, and the size of the orbit will be exactly half of the size of the group. Because each of them will get twice. And so on. And so this is the meaning of that. Because, okay, so maybe you can't recall this. So this is the index of Gx and G, which is defined as the number of cosets, okay, of Gx and G. So you look at the group G, you have to subgroup Gx, and then, okay, no, sorry. You have the subgroup Gx, it's better to think about it like this. And then you have some other G times Gx, and then you have some other G2 times Gx, and so on, and these will be all the cosets. And now what we're going to prove, and I was wasting time, so we're only going to prove it next week, is that there is a bijection between the cosets and these elements. Okay? And then actually, well, we made it sort of clear. It's just a technicality to prove that this bijection is there, because what we're doing is, you look at all, so Gx, that's the subgroup, there's all the elements of G that leave X book. And then another coset, that's all the elements of G that move X away. And then there's another coset, and that's all the elements of G that move X away. this is the idea. And that's all I've got. So, any questions?
I think I made it too simple.